All right. Let's see. This is a formula pretest for your formula test. So, point of this is to try and see if you really know your formulas that I've been letting you use on your practice test that you won't generally have on the AP test. So, hopefully you've tried this. I'll just go through and show you what I'm expecting, just in case you don't realize. Maybe you think you have what you should have, but so some of these are just antiderivatives. So any of the antiderivatives are fair game. I think there's like 15 of them or something like that. So, and you got to realize this is just, another way of saying take the derivative, and the derivative inverse sine is 1 over the square root of 1 minus x squared. They could be written in kind of a u form. Now, this is an antiderivative, so that's a derivative. This is antiderivative. Inverse tangent of u plus c. Got to remember the plus c. 19th derivative sine. Well, that probably means there's a pattern. So you'd be like, well, this is the 0th derivative. And the first derivative is cosine. And the second derivative is negative sine. And the third derivative is negative cosine. And the fourth derivative is positive sine. And now we're back to where we started. So there's these chunks of 4 that get repeated. So the strategy here is to figure out, well, how many full chunks of 4 are there? Because let's just ignore those because we'll be back at the beginning. So we take the 19 divided by 4, and that goes in 4 times, and that's 16. So those are all the full chunks of 4 that we've finished, and the remainder is what we care about, because that means, well, we're going to be on the third derivatives. So the 19th derivative, which a lot of times we'll write like that superscript inside parentheses, equals the third derivative, which is negative cosine x. Now, if you get a remainder of 0, that means you're at the 0th derivative, the original function. Okay. I also put some basic trig in here, just so you know. There's a lot of trig. Root 2 over 2. Cotangent is the opposite of tangent. That's 1 over tangent. And tangent is sine over cosine, right? So that's sine over cosine. So then we end up getting cosine over sine. And then the angles, remember, signs like this. So you get 0, pi over 6, pi over 4, pi over 3, pi over 2, 1/2, root 2 over 2, root 3 over 2. So we're at pi over 3. That's pi over 6, pi over 3. That's root 3 over 2 for sine. And we're in the first quadrant, so it's positive. Cosine has the same values, but it goes from the top to the bottom. So pi over 6, pi over 4, pi over 3, root 3 over 2, root 2 over 2, 1/2. And so then your answer is 1 over root 3, which you could then rationalize the denominator if you like. Not a requirement necessarily, but multiple choice might ask you to do that. Secant is 1 over cosine. So my trick for all that they call these reciprocal trig functions is that it's always a co with a non-co. It's one equals another one of the basic ones upside down, but it's a co with a non-co. So secant goes with cosine. Cosecant goes with sine. Tangent, cotangent go together. Okay, so now cosine of pi over 6 is root 3 over 2. So we're going to get 2 over root 3 or 2 root 3 over 3. Either one is fine with me. Tangent. Now you might be like, oh, yeah, tangent. I know that one. That one's secant squared x. No, you're going the wrong way. You just took the derivative. We're trying to undo the derivative. So this is not one we've memorized. So sometimes with trig, what you should do is get creative and rewrite them in sine and cosine or the other way around, and then try maybe like u substitution. U equals cosine x, du equals negative sine x. So usually a denominator is a good choice for your first choice of u. Don't miss that negative. So this is going to be negative du over u. It's going to be negative natural log the absolute value of u. So it's going to be negative natural log the absolute value of cosine x plus c. Can we get rid of those absolute values? Is cosine always positive or always negative? Nope. So some quick rules there. 7, express f prime as a limit where x goes 0. So essentially, I'm asking for the definition of the derivative. So everything in calculus comes down to limits, and f prime of x equals the limit as x goes to 0 of the difference quotient. It's just rise over run. So it's f of x plus h minus f of x over h. It's changing y over changing x. Then we're going to make the x go to 0. We're going to make the points get infinitely close to each other. This is the definition of the derivative. I need the limit. I need all of that. Now, there's some other versions of this we wrote. That's a right-sided approach. I guess we could write the other ones real quick right here, because sometimes they might give these to you, and they might not give you this common one here. We could do a point and a point to the left. And we get just an h on the bottom. You could do a symmetric, a left and right side. So you do to the right, fx plus h, minus to the left, x minus h. So you pick 2 points that are on either side of the point you want, close to it. But then you got to divide by 2h, because there's 2h space between them in the x direction. Number 8, this is just power rule. Bump it up 1. Divide by the new exponent plus c, right? Next one is quotient rule, right? So low d high minus high d low all over low squared. Cotangent. So I remember these in pairs. So tangent is secant squared, right? And cotangent, any trig that you take derivative of that has co in it, it's going to be negative. And so instead of secant, it's cosecant squared. This is a chain rule issue. You got to take the derivative of the outside first, leave the inside the same, and then multiply by the derivative of what's inside. So we got to use that all the time. Find the average value. So does it say average value of the derivative? No, it just says average value of p. So this is mean value theorem. And we say, well, let's find the area under the graph. Smooth it out. Make it a rectangle. The height of that rectangle is what we want to be the average height, the average value of the function. So we got to divide by the base of the rectangle. So there you go. Got some rectilinear motion stuff on here. Velocity is the integral of acceleration, right? It's the integral of the derivative of velocity, which is acceleration. The derivative of position is velocity. You need to know how to work forwards and backwards from acceleration, velocity, and position from one to the other. Displacement is the integral of velocity, because that gives you just the overall change in position, x prime. Distance, we force all the negative changes to be positive and add them all up, so we get a total distance. So you need absolute value of velocity, or speed is what's there. I mean, this is what I want in your work. 16 says if Johnny's velocity is negative 2 feet per second and his acceleration is negative 3 feet per second squared, then he is speeding up or slowing down. Speeding up, they go in the same direction, right? They're both negative. That's the thing that matters. Now, not every this is just an example of what the test could be like. Any of these ideas from any of these topics are fair game. Even any derivative rules I didn't mention here, any anti-derivative rules I didn't mention. These ones here, state the theorem. So 1, you got to answer the question, and then 2, you need to state the theorem that applies to each answer. Okay, so there's 2 things I need for each of these. If fx is differentiable on a to b, then there must be at least one c on a to b where f prime equals, this is mean value theorem, and we're obviously talking about derivatives, so it's going to be f of b minus f of a over b minus a. This is f prime average, right? And the other part of the mean value theorem guarantees that the actual slope will equal the average slope at some point c between the endpoints. So that's part of your answer. F prime c equals fb minus f of a over b minus a. And then the theorem that applies is by mean value theorem for f prime of x. I want all of that. I don't want the initials. You can write the initials down for your own just notes, but I, on this test, want to know that you actually know what these letters stand for, because I think sometimes people don't, and that's not going to be good for free response, because initials and free response won't be good either. 18, what theorem guarantees an absolute minimum for a continuous function on a closed interval? Well, that's extreme value theorem. So that's a one answer one. Extreme value theorem. 19. You might look at this and be like, oh, we're integrating the derivative, right? So the way I usually start with this is if I integrate the derivative, I get the original function, and then I plug limits in, top first, bottom second. And we use this a lot of times when we have information about the derivative, information about a single point, and then we want to find another point. So we're trying to find this one, so that means we're going to add this one to the other side, right? And that's what we're putting right there. So the answer is f of a. The test or theorem is the fundamental theorem of calculus, part 1. Fundamental theorem of calculus, part 1. I want you to write it all out. I want the part 1 also. Okay? 20 says f of x is differentiable. If it's differentiable, and you know that fa and fb both equal 0, then fx must have at least one critical point on a to b, true or false. Now, these true false ones, I want you to give me evidence to support it. Critical point is where f prime equals 0 or undefined. You say, well, can we know for sure that it equals 0 somewhere between a and b? Now, these aren't derivatives. These are the actual values of the graph. So if you're guaranteeing that the derivative is going to equal a certain value at some point, this might be mean value theorem for derivatives, right? And so we might say, well, let's find the average derivative. That'd be fb minus fa over b minus a. And they've told us that each of these equals 0. So we get 0. Which means guaranteed by the mean value theorem that the actual derivative will equal the average derivative at least once. At least once, which means we will for sure get a critical point. So the answer is true. Okay, you have the work now to support it. The name of the theorem is by the mean value theorem for f prime of x, or for derivatives. But I need this work right here to support it. This one says true or false. The second derivative, average second derivative equals f prime a minus f prime b over a minus b. Is that true or false? This is we're treating it as a derivative. This is mean value theorem for derivatives. Now, I feel like I usually write it f. Now, if f double prime is the slope of f prime, so we're trying to find the average slope of f prime, I usually write it like this. Do you have to? No, slope, rise of run, this is what this is, can be, you can start at either point, you just got to be consistent on the top and bottom. If you start with b on the top, start with b on the bottom. So this is true. It's not necessarily work to show. And by the mean value theorem for f prime of x. So that's what I'm looking for in those. 22 says f prime of x is greater than 0 when f of x is increasing or decreasing. F prime of x is greater than 0 when f of x is increasing or decreasing. So it's a question. Increasing, right? Increasing. If f of x is decreasing, then a right Riemann sum will be an over-under estimate. Well, you could just draw a picture right here, decreasing, right? And I draw my little lines. It's decreasing. It's got to be going down. A right Riemann sum. This is your curve, by the way. A right Riemann sum. Now, really, you just need to do one slice. But this is clearly an underestimate, right? Underestimate. But you can just draw a picture. You can just draw a picture of one slice. You'd be like, all right, here's one slice of a decreasing function. I'm going to do a right Riemann sum. It's an underestimate. Done. Easy. So I don't even memorize those. I remember that increasing, decreasing has to do with the left and right Riemann sums, and concavity has to do with midpoint and trapezoid. 24. If f of x is differentiable and f prime of 3 equals 0, so we have a critical point, and f double prime of 3 is less than f prime of 3, well, that means f prime 3 equals 0, so that means that f double prime is negative, which means that it's concave down. Then f of x has a relative maximum or minimum. Well, it's concave down, and it has a critical point, right? So that's a relative max. I don't memorize that. I just draw a little picture or picture in my head. So this is a relative maximum. So the answer is relative maximum. I'm going to complain if you just say maximum, because maximum without relative in front means absolute, and that's not true necessarily. By what? So there's a second part of the answer. This is the second derivative test for relative extrema. I want that whole answer. No initials. I need the for relative extrema. Sometimes people just say second derivative test on things where they're not looking for relative extrema, so it might be good to remember that's for relative extrema. 25, area of the region R. Well, probably going to do like vertical slices, y top minus y bottom. And so we're going to say that the area equals the integral a to b. Top is gx, bottom is fx, and dx. You need parentheses around the whole thing. You got to do g minus f. You need the dx. If you're missing any of those things, I'm taking off points. Volume of solid in R is revolved around y equals -2. So y equals -2 would be like, I don't know, something down here. So we revolve it. And I think we're going to just do, vertical slices, because there's no way we're going to get g in terms of y, right? Or x in terms of y. So this is the original region. This is your big R. This is your little r. And so the volume is going to be pi big R squared dx minus pi little r squared dx. And so for us, it's going to be pi. Now big R, now we're going left to right, A to B. Big R is y top minus y bottom. Y top is gx. Y bottom is negative 2 squared dx minus pi A to B. Little r is the bottom curve, is the top y top for that one, fx, minus negative 2 dx. Now you could write that as plus 2 if you want. Simplify it. But this is what I'm looking for. You need parentheses, you need the squareds, you need the pi, you need the limits, you need the dx. 27. The volume of a solid R as base and cross sections perpendicular to the x-axis are a semicircle. So we're doing volume by cross section, right? And so the volume, we need some area formula. We need it's a half circle. It's 1/2 pi r squared dx. Now this is the diameter, so half of that is the radius. So our answer is going to be volume equals pi over 2 integral a to b. It's going to be gx minus fx, y top minus y bottom. That's the diameter, so we get divided by 2 before we square it. So you need these parentheses around it with the division by 2. If you like, you could simplify this to pi over 8, a to b, gx minus fx squared dx. And that's up to you. I don't care. Either way. So I'm looking that you know how to set these up. 28. Antiderivative of 1 over u is natural log of u plus c. You need the absolute values. Antiderivative of e to the u is e to the u plus c needs plus c. What's the derivative of b to the u? Well, the derivative of e to the u is e to the u. B to the u is like that. E to the u is a special case of this. So it's b to the u. This one's a little hard to remember because we don't use it that much. Times natural log of the base. Okay? But then here's another thing. Since I put u's here, we need an extra du dx because this is like a chain rule, example. So that whole thing, no plus c. We're not going that way. 31 says sketch a natural log function. I want all the important things. I want vertical asymptotes. I want it to look right. I want any x or y intercepts labeled on it. Okay, so I need all of that. I need vertical asymptote labeled, x-intercept labeled, sketch negative e to the x. So remember, e to the x looks like this. Negative e to the x gets flipped upside down. It has a horizontal asymptote, y equals 0. This y-intercept is usually 0, 1. It is now 0, negative 1. And so that's what I want for that one. I want all the important things labeled on those graphs. That's it. This is what a formula test would look like. Just making sure you know your formulas. You should do this without having to use your formula sheet. You've got to test yourself, make sure you're ready to not have any formulas.